Tu veux tester le son? C'est bon?
Allô, 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 c'est bon.
Ouais, ouais.
Aujourd'hui, nous avons le plaisir d'accueillir un ancien du laboratoire, Thomas, qui a fait sa thèse ici avec Tarané et qui est ensuite en ce moment parti en postdoc à l'EPFL avec François Galère. Et aujourd'hui, il va nous parler de rebondissement et de ballottement des simulations numériques au modèle réduit. À toi, Thomas.
So I'm going to do my presentation in English. Hi everyone, thank you for coming. Today I'm going to talk about two things we're doing during my postdoc, maybe three if I have some time. Mainly on the bouncing drop, so drop bouncing on a vibrating stage, and on the mean flow induced by orbital motion in sloshing. So let's start first with some motivation. Why do we do numerical simulations? So in my view, numerical simulations can help us bridge the gap between complex phenomena and reduced models. They can work with experiments, provided that the methods are accurate enough, and this means that you need to validate a method to be sure that what you see corresponds to the reality. Of course, the complexity of a considered phenomenon can lead to development of novel numerical techniques, right? If you consider very complicated systems, in particular two-phase flows with the phase change or contact lines, or even in microfluidics. Now, on the other side, reduced order models are very attractive because they can grasp the physics and the mechanics of the system based on theoretical relations. And so the idea is that we can use large data sets from experiments and simulations, and in conjunction with the theoretical considerations, to construct such reduced models. Or the other way, we can assess the validity of pre-existing ones. So as an outline of this talk, first I'm going to talk about bouncing, a liquid drop that bounces over a vibrating stage. Then about sloshing, where we want to model the wave-induced mean flow in orbital sloshing. And then a very short presentation of the last subject about braking in T-junctions. So let's start first with bouncing. This is a work done in collaboration with Lebo Molefe, François Galère, and John Koliski, all at EPFL. So I start first with an experimental observation. We have a drop that falls on a vibrating stage. This is an oil drop. You have the physical parameters here. The corresponding dimensionless numbers, which are the Weber, the Bond, and the Ohnesorg number, are listed here. And basically in this regime, we expect the drop to bounce even without vibration. The drop will not splash. And so what happens is that there is always a thin air layer between the drop surface and the stage that mediates the interaction between the vibrating stage and the drop. And so the stage vibration here is written as a harmonic forcing with a certain amplitude, AS, and a certain frequency, Fs. So here we are at 40 Hertz, and you see the drop bouncing off the stage. You see a clear air gap that is forming at each rebound. And what happens if you increase the frequency? So now same system, but I just increase the frequency to 180 Hertz. You see a different regime, which we call bound, where you see the drop that is bound to the stage, to the vibrating stage, right? It is no longer bouncing off the stage, and you see different shapes that enter at play, right? You see these alternating triangular shapes. And what we wanted to understand is, can we rationalize this behavior? So the first thing that we did was to conduct experiments. So what we did first was to fix the stage amplitude and vary the forcing frequency in order to cast a resonance curve. And what we are monitoring is simply the mean drop amplitude. So we are looking at the mean displacement of the drop center of mass. And you can see these experimental points. So we are looking at AD as a function of the frequency. You might see first a peak here around 30 Hertz, then maybe a second one here with a bit of spread. So these dashed lines corresponds to a fixed frequency, but different phase, initial impact phase, right? And then you can see also that above a certain value of the frequency, the drop amplitude is very low, right? And this corresponds to the bound case I showed. And so the question here that we want to answer is, can we rationalize this resonant behavior and try to construct a reduced order model that could predict these trajectories? So what we do first is we do some simulations. So we use Basilisk free software to solve the two-phase incompressible Navier-Stokes equations. We are in the frame of reference of the moving stage, so we have a modified acceleration term here in the continuum equation. And this bond number, this modified bond number, is simply the gravity. So the gravity here is 1, plus the forcing with gamma the dimensionless acceleration, and omega the vibration number, where here simply omega s is the angular forcing frequency, and omega d is the natural frequency of the drop, or Rayleigh frequency. And here are just two examples of numerical simulation in axisymmetric form, where you see that for 40 Hertz, you see a bouncing drop, right? You see a clear air gap that is forming at each rebound, which is not the case in the bound example, right? At higher frequency, where you see these alternating triangular shapes as we saw in the experiments. So what we can do is we can first assess the validity of our numerical method, right? We want to compare for two given cases, the experiments and the simulations, to be sure that what we see corresponds to the reality. And this is precisely what I'm showing here. So on the left, we have a bouncing example. At the top, it's the chemograph, so the experimental chemograph of the drop, so time on the x-axis and z on the y-axis. You can monitor first the drop center of mass, which is the green curve, the experimental drop center of mass. And you can superimpose the DNS counterpart in dashed lines. You can see that it matches quite well. And you can also see that in this case, you have this air layer, which is this gray area that is formed at each rebound. So here the drop is really bouncing off the stage. Moreover, what you can do is you can also monitor the drop deformation as a function of time. So you can look at the variation in percentage of width and height, which is here in yellow and in red. And you can also superimpose what you see in the DNS, and it matches quite well. Here you see that you have huge deformations at each impact, and you see that then when it lifts off the stage, it will tend towards its equilibrium shape, but maybe when it comes back to the stage, it's not yet at equilibrium. So this is something that gives us already a hint of how to understand this phenomenon. Then on the bound case, you see that you have very little center of mass displacement, right? You're really locked onto the stage vibration. There is still an air layer between the stage and the drop, of course. And you see that the drop here is always deformed, and the deformation also follows the vibration frequency. Now, what you can do with the DNS is you can look a bit further. You can monitor different things, right? And one interesting thing to do here is to cast an energy budget of this system. So the initial drop at a certain height has a potential energy, which is defined by its position, kinetic energy, which is 0 at T0, right? And the surface energy that accounts for the drop shape. So the total drop energy is simply the sum of these three energies. And then what happens when the drop enters in contact is that you have viscous dissipation, which is written here in D. And you also have the work exerted by the stage. So you have energy injected back to the drop by the stage through the air layer. And so you can monitor this for different cases. On the top, you have a bouncing case. So the drop starts with a certain potential energy in blue, 0 kinetic energy in red, and a certain surface energy in yellow. And the moment it contacts with the stage through the air layer, again, so there is no real contact, you see that the surface energy increases a lot, right? Because the drop is deformed. You see that the kinetic energy goes to 0 as the center of mass doesn't move anymore. And the potential energy is also minimal. and then it, because the stage is is able to counteract the viscous dissipation occurring at touchdown, the drop is able to lift off the stage, right? Here you have the same example for the bound case, where you see that this total energy of the drop is not increasing after first impact. It means that the drop is no longer bouncing. So in these two cases, this is a low energy bouncing mode, right? Because you could think that if you inject enough energy to the drop, then the total energy of the drop would be higher than 1. It means that for a drop, it could go higher than the initial position. So its energy would be higher. Now, this highlights the importance of the drop surface deformation, right? This is really important if you want to model this phenomena. Now, what we can do is we can come back to the resonance curve that we showed, right? Initially, I just showed this resonance curve only with the points, so only with the experimental data. And what you can do is you can run simulations and do this for different drop sizes. This is to account for the experimental spread, right? When you generate a drop with a syringe, you're not sure about the diameter, so there is some experimental spread. And what you see is that if you look at the mean amplitude of the DNS, it matches quite well the experimental points. And moreover, you're able to explain this experimental spread here with this orange area. And this is highlighted in the bottom plot, where we show a phase diagram of the drop mean amplitude AD as a function of the forcing frequency and the phase, the initial impact phase. And so what we see is that around this area, the mean drop amplitude depends on the impact phase, right? If the stage is going down at the moment the drop touches the stage, then we will have a high rebound amplitude. But it's not the case if the stage is going up while the drop is touching it, right? So this explains the experimental spread. And then what you see is that above a certain threshold, which here are these vertical lines for each drop radius, you see that the drops are bound. And this is also highlighted here, right? You see that the mean amplitude is very low above a certain threshold. And so the idea here was to try to understand what's this threshold, what's the mechanism at play, and what drives this resonance behavior. Yes, of course, I'm also going a bit ahead of myself here by saying that if you recast this dimensional plot into a dimensionless one with the vibration number here, you can see that the curves for different radii around this transition zone collapse, right? So this is also a hint that something is happening here depending on the drop size. Now, what we want to do here is we want to try to parameterize the drop shape and deformation as a function of time. So the idea is to decompose the drop into a spherical harmonic, assuming an axisymmetric profile, right? And so basically the radius of the drop is a function of theta, the angle, and time. And we have here the sum of the spherical harmonic modes. And the sum starts at 2 because the 0 violates mass conservation, right? It's simply an extension like this. And the first is a simple translation, and we don't consider it because we are in the frame of reference of the moving stage. And so in practice, what we do is we fit these equations and we find the coefficients A from 2 to infinity. But in practice, we fit only up until 10. And we find that only the first few contribute to the deformation. And here are some examples of the 2, 3, and 4 mode of deformation with positive and negative values of the coefficients. So this is precisely what I'm going to show here. We have these modes of deformation. And what we can do is we can look, for example, at a bouncing case, and we can monitor the dimensionless mode amplitude AL for the mode 2, 3, 4, and the same thing for the bound case, right? So for the bouncing case, what you see is that the second mode is highly excited at touchdown, right? It's the predominant one. And for the bound case, you see that the amplitude of the second matches the third one. So this relates to these triangular shapes that we saw in the experimental video, precisely this mode of deformation. And then what you can do is you can look at the average peak of each mode amplitude of these deformations as a function of the vibration number, so the frequency. And you can see that the second mode is predominant up until a certain point, where the third one starts to grow and the second one starts to decay. And this is the region where we have these bound drops. So motivated by this, and by also previous work on similar setups. So a lot of people have worked on drops on vibrating liquid bath. Here I just cited a few, but I would need 10 slides to cite all of them. We wanted to try to construct a reduced order model that could predict these trajectories. So in particular, in the paper of Molacek and Bush, they have this model where they consider that the drop is a simple sphere, right? And that the deformation only occurs in the bath, right? So it's the bath that is deforming and not the drop. And they have this very nice linear spring where they can predict the position of the center of mass Z by solving this simple damped oscillator. And you have a drop liquid interactor that is here with this heaviside function. So anything that happens here only happens at the moment of contact. And what they say is that this behaves as a damped oscillator, and they have two coefficients, D and C, that are related to the coefficient of restitution and the time of contact. Now, they also have another model which is a bit more involved, which accounts now for the deformation of the bath. They have three constants, C1 to C3, that they can fit their experimental data with. So the idea is that based on these models and on the identified mechanism in our case, so remember that in our case, it's not the bath that is deforming, but it's the drop, because our solid stage has, of course, zero compliance. Based on this, can we try to cast a reduced order model and without any fitting parameters, right? And the main idea is to say that we could couple the center of mass to the simplest description of the drop shape, which is by using the second mode of deformation. And so this is the coupled linear spring that we developed. So on the left, we have the center of mass, and on the right, we have the drop deformation only modeled through the second mode of deformation. The top row corresponds to no contact, so when you are away from the stage. So away from the stage, the center of mass is simply a free fall, but you are in the frame of reference of the moving stage, so you have this modified bond number, right? So if you would see the drop moving like this, if you would be in the lab frame of reference. And then for the second mode of deformation, you have this simple spring, which comes from these seminal papers, where the coefficient B2 is the dissipation coefficient of the second mode, and omega 2, which is equal to square root of 8, is simply the natural frequency of the second mode. And precisely this square root of 8 was the cutoff frequency that we found that distinguished the bouncing to the bound state. Then what happens when we enter in contact? So when we enter in contact, the idea is similar to the one of Molacek and Bush. We want to say that we have now a damped oscillator, but what we say is that the dissipation only occurs through the second mode of deformation, so that the dissipation coefficient is the same here than here. And we say that there is also a forcing of the stage on the center of mass, which is written here by the Z star, but now accounting for the drop deformation A2. So now we have a one-way coupling, right? We have A2 that is coupled in this equation because this Z star depends on A2. Now, we need to force the second mode of deformation, the amplitude of the second mode of deformation at the moment of contact. And this is done by adding a forcing term that was derived in another paper by Molacek and Bush that consider a quasi-static approximation of drops on different solid substrate. And basically, this depends on the instantaneous acceleration exerted on the drop and also the surface area, which is here alpha over 3. Now, our model looks like this. We have a drop that is falling also with this modified bond, right? But now we consider its deformation. The solid is no longer deformed, as in the Molacek and Bush previous model. And the drop stage interactor is only activated when Z minus A2 is below this dashed line, right? When you are above, you still have this air gap, so the drop does not fill the stage. And this is written here, where H is the heaviside function that triggers or not this coupling based on the sign of this Z star. Now, what we can do is we can take this model and take some simulations that we did with the Navier-Stokes solver. We can look at the predictions of the DNS and the predictions of the model. So again, here we have no fitting parameters, right? Every parameter depends on the system properties. We look here, for example, first at low forcing frequency, so 20 Hertz. Here we're not even bouncing. We see that there is no air layer between the drop and the stage. We see that the center of mass is hardly displaced. In solid lines, we have the DNS, and in dashed lines, we have the model predictions. We can also monitor the drop deformation as a function of time. Now we can increase the frequency. So at 40 Hertz now it's bouncing. The model can still predict this bouncing motion. We can predict the deformation of the drop as a function of time. And you can repeat this for a lot of frequency. Here at 60 Hertz, it's a case of a bound drop, right? We are in this phase-dependent spread. Now, if we go a bit higher at 80 Hertz, now we are again in a bouncing mode, right, where we see this air layer. Again, the prediction of the model are very accurate and allow us to also predict the drop deformation. And then if you are at very large frequency, you are beyond this bouncing to bound transition, and so you are in a bound case, which is also predicted by the model. Now you can do a more systematic evaluation of this. You can look at a phase diagram of the drop mean amplitude as a function of the vibration number and the dimensionless acceleration. So here the color map is simply the AD, the dimensionless drop mean amplitude. And you can also superimpose the experimental data, which are the points here, and the color of the points correspond to the mean drop amplitude. So here is what we see when we run 10,000 DNS results. You see this transition here from bouncing to bound. You see a cutoff around square root of 8, which is the natural frequency of the second mode of deformation. You also see that at around the natural frequency of the drop, so omega 1, at high acceleration, you see a period doubling cascade here, so very high mean amplitudes. And now you can do the same with the model. And so this is what is predicted by the model. It's very similar. We are able to recover this bouncing to bound transition. We are also able to recover this very high mean amplitude here around omega 1. What you can see, one of the differences you can see is that the lines here, so the contours are a bit more straight. And this is explained by the fact that here we are neglecting the third mode of deformation, right? We only have the second one. So it's natural that we don't have this bending of these contours. So now, as an outlook of this first part, what we can also show in this system is that we have a higher mobility than on a liquid bath. So if you take the same system, you put a liquid bath and you tilt your stage, right? The drop will move laterally. And what you see is that when you do that with a liquid bath, the drop moves very slowly, right? These are experiments. Now, if you do the same with the stage, so you remove the liquid, you see that the drop moves laterally faster than with the liquid bath. And so you can do also simulations on this. You can tilt your gravity. You can have a periodic box. And you can show that the drop on the right side, which is bouncing of a vibrating stage and there is no liquid bath, is going faster than the drop on the left side that is on the liquid bath. So here, for the simulations, what you do is that you impose no coalescence between the drop and the underlying liquid. So of course here, this is a periodic box, right? You would need a very large domain to be able to accurately simulate this. These are just preliminary results. Now, let me move now to the second topic of this talk, which is the modeling of the wave-induced mean flow in orbital sloshing. This is done in collaboration with Alessandro Bongarsone, Alice Marcotte, and François Galère. And so the idea here is a bit different than what I showed previously. We know that orbital shaking of a partially filled container is common to a lot of applications, and basically this can prevent sedimentation or enhanced mixing. And what we know is that away from resonant conditions, we have a small amplitude rotating wave that produces a mean flow under this motion. So here is the sketch of the system we are looking into. We have a cylinder that is filled with some liquid, and we have a rotating motion. And so what was shown in their experimental paper by Bouvard and Frédéric Moisy is that there is a Lagrangian mean flow that shows global toroidal. Toroidal is the horizontal cut here, and poloidal mean flow. And in the poloidal one, you see recirculations close to the contact line. And so the idea is that this Lagrangian mean flow can be decomposed into an Eulerian mean flow and a Stokes drift that accounts for the slight variation of wave magnitude. And so what we want to answer here is, can we model these mean flow contributions using two different techniques, so weakly nonlinear analysis and direct numerical simulations. And in this case, we will use DNS to cross-validate what is predicted by the weakly nonlinear analysis. So let me go back first to the flow configuration. We are looking at this partially filled cylinder with a certain height to radius ratio. We are going to vary the viscosity. We're going to see the effect of the viscosity on the generated mean flow. Here it's simply the rotating motion with a certain amplitude and a certain forcing frequency. Here omega-1 is the lowest natural frequency of this system, and this is useful to make everything dimensionless. And so the dimensionless numbers that appear in this system are simply the aspect ratio, the dimensionless forcing, the Froude number, the bond number, and the Reynolds number. And so the Froude number and the bond and the Reynolds number are going to change as we vary the viscosity. So we have two methods, and we want to see if we can predict what is seen in the experiments. So first, I'm going to start by the weakly nonlinear analysis. We are in cylindrical coordinates. We solve the incompressible Navier-Stokes equations, and we have a forcing term here that accounts for the fact that we are in the frame of reference of the rotating cylinder. Now, what we have is we have a kinematic boundary condition, so no flux is allowed through the interface. We have the Laplace law that relates pressure to curvature here. And in particular, what was done here by my collaborators is that they added a localized slip model. So what they do is that they have a no-slip wall everywhere, except around the contact line where they allowed for some slip. And so the idea of this is that you can decompose the flow field into a linear time harmonic sloshing wave and a second order Eulerian mean flow. And so I'm not going to go into details on this because this is not the topic of this part, but it's more on how can we try to cross-validate what was predicted here. So on the DNS, what we do is we do a very similar thing that previously, but now we are in 3D. My forcing now is a bit different, but it's very similar, right? I'm still in the frame of reference of the rotating cylinder. What we need to do now is we need to model this solid wall, right? So what we do is we use the embedded boundary method. So this is still with Basilisk. And to do so, we use the Johansson-Colella method that is used to compute the phase gradient of a scalar quantity on this embedded surface. And this is a sketch from Mathilde Tavares' paper, where they also studied these, where they tried to apply different boundary conditions on these solid walls. Moreover, we can also apply a constant contact angle here by simply setting the normal of the interface to the wall such that we have the prescribed static contact angle theta s. So later I'm going to go back to this method, but first now let's try to compare the experiments with the weakly nonlinear analysis with the DNS. So what it looks like in the DNS, so we have here, for example, a given Reynolds and a bond number and Froude number. We are at relatively small forcing epsilon. We are away from resonance. And if you have grid sizes that are around 500 micrometers, you have 200 points per diameter. And so 4 points per boundary layer. And this is what you see. So time goes from left to right. You see the sloshing wave. So here I'm looking at the free surface. And I'm coloring it with the horizontal velocity magnitude. And you see that is rotating counterclockwise. So what you can do first is you can look at this instantaneous sloshing wave. So you can cut your system below the surface at this height, z over r equals minus 0.23. This is a precise number because we want to match precisely what was seen in the experiment. So in the experiments, they see these two cuts for two different viscosities. So low viscosity at the top, high viscosity at the bottom. The weakly nonlinear analysis is able to predict also this sloshing wave, and it's also the case for the DNS, right? So this is the first order check that we want to do, right? So if you're not able to do this, you cannot accurately predict a mean flow. What you can also look at is you can look at the norm of the horizontal viscosity. So you look at this z at this cut, you look at the center of your domain, and you monitor the norm of the velocity of the horizontal velocity after the transient. And what you can do here is you can show this resonance curve. So you have a fixed amplitude and you have a varying frequency. And you see that the DNS is able to mostly capture what is seen in the experiments, closer to resonance. And of course, linear analysis here fails close to resonance. What you can do is you can do the same, but you can fix the forcing frequency. So 3 different force field frequencies. The squares are the experimental data. And you can vary the amplitude. And you can see that the DNS also matches quite well. And in particular, you can match this saturation here with these purple stars. And so now what we want to do is we want to try to characterize the mean flow away from resonance. So we are around here, right? Here it corresponds to this point also. Now, let me go back to this mean flow characterization. So we have a Lagrangian mean flow that can be decomposed into an Eulerian contribution and a Stokes drift. And so in experiments, what they do is they do SPIV, and they can monitor this Lagrangian mean flow. In the weakly nonlinear analysis, you can compute directly the Eulerian mean flow and the Stokes drift. And in the DNS, what we do to compute these two contributions is the following. So the Eulerian mean flow is simply a time average of the velocities over one period. So we take a picture, right, in any cut of the velocities at each time step, and then we average over one period. And to compute the Lagrangian mean flow, what we do is we inject some Lagrangian particles. We let them move for one period. We look at their position one period later. And so we have 2 positions. We divide by time, and we have a velocity. So we can distinguish both contributions. So let's see how it looks like. So on the top, I'm looking at the toroidal mean flow, and on the bottom, the poloidal one. This column corresponds to the experimental results. You see that we have a co-directed here Lagrangian mean flow with the wave. And also you have these structures close to the contact line. The weakly nonlinear analysis is able to capture precisely that, right? The qualitative agreement is very good, specifically here for the toroidal mean flow. And this is also the case for the DNS, right? You see the same structures, you see the same structures here also for the toroidal one. And the question now is, so the experiment only have the Lagrangian mean flow, and what we want to see is if the decomposition of these 2 methods agree. And so this is precisely what we do here. On the top row, we have the weakly nonlinear analysis. On the bottom one, DNS. We have here the Lagrangian mean flow in toroidal Lagrangian mean flow. We can decompose it into an Eulerian mean flow, and here you can see that the structures agree quite well, right? You have this co-directed Eulerian mean flow, and then you have also the Stokes drift contribution, which also agrees quite well. Now you can do the same for the poloidal decomposition. You have the Lagrangian mean flow for these 2 methods. You can decompose them, and they agree quite well. It's a bit saturated here. It's very hard to model this, right? Because here we are looking at order 2 quantities, which are very sensitive to any numerical noise. Now, what happens at low viscosity? So here I'm only showing DNS results, right? So far we were at high viscosity, but at low viscosity we see the following. So we have this Lagrangian mean flow, right, which is a bit different than the previous one, but it's still co-directed with the wave. But when you decompose it, you see that the Eulerian mean flow is now counter-directed with the wave, right? It's rotating the other way, and you have also this Stokes drift contribution, which is co-directed. So far here we have assumed that we have a no-slip wall on our DNS, and we just apply a constant contact angle. But we know that the dissipation at this contact line is key in this generated mean flow. And the idea here is to use very common techniques or models in continuum mechanics by introducing a small slip length at the contact line using the Navier boundary condition. And this is what's written here. So lambda here is the slip length. So this is trivial to do in a 2D domain or even 3D domain where you apply this on the walls, because your tangential and normal components are aligned with your Cartesian grid, right? So x is the tangential and y is the normal. But it's not trivial when we do this on arbitrary geometries, even more so in 3D. So there's a lot of people working in this precise subject. There is Jacob Marek, there is Mathilde Tavares, there is Pierre-Antoine Maez also in Aachen that is working on this. And the idea here on the next few slides is to try to convince you that we can solve this problem by a simple linear algebra. So the idea, let's start first with a simple boundary condition. So a Dirichlet on a solid boundary. Let's imagine, for example, a plate that is not aligned with my Cartesian grid and that is moving, right? So we have a certain tangential velocity u, and we also have a no penetration boundary condition. So there is no flux through my solid. Now what you can do is you can decompose this tangential component and normal component into Cartesian components, And it's simply the x component times the x component of the tangential vector and the y component of the tangential vector, and so on. And the same thing for the normal. And with this, you can cast a very simple linear system, which is invertible. And what you can do is you can find an explicit relation, solution for the values of ux and uy that you need to apply in your Cartesian coordinates, such that the continuum boundary condition is fulfilled, right? So if you apply this, then this is true, right? So here it's very simple, right? I'm just rotating my system. My boundary condition is easy. So what happens now if I'm using the slip boundary condition? So now I have an extra term here in the tangential, the condition for the tangential velocity. But let's assume now a simpler case. So harder boundary condition, but simpler case. I'm aligned with the mesh. That means that my tangential component is x and my normal is y, right? So these two are not coupled. I can do the same thing. I can write this in x and y, right? But because I have ty and nx equals to 0, it's only ux at the top and uy at the bottom. And what I can do is I can replace the normal gradient of the velocity by this Johansen-Colella method, which was used in the embedded boundary. And so the idea here is very simple. Is if we replace this term by the Johansen-Colella discretization, you can put every unknown on the left and every known on the right, and you can cast a linear system, right, where we could solve for these two quantities, ux and uy, which are the unknowns. Here it's decoupled, right? You have two zeros here. It's decoupled because we are in the mesh-aligned case. In the mesh-aligned case, x is tangential and y is normal. And so you find that, indeed, if you just impose this value at the x component of the velocity on each fragment of your solid, then this boundary condition is fulfilled, right? And uy is simply 0 because uy is the normal. Now, what happens if you're not mesh-aligned? Well, if you're not mesh-aligned, it's the same. But now you have two contributions on your gradient. You have the x and the y contributions, but you can still write this linear system. It's a bit more involved, but it's completely trivial, right? It's a 2x2 matrix. You can solve this. This is invertible. And what you can see is that you have an explicit solution for the two components, ux and uy, that depend simply on the interpolated values I1 and I2 that are used in the Johansen-Colella method. So everything here is known at each time step, at each point, and you just impose this. And by imposing that, you fulfill this boundary condition, right? So 3D is the same, right? I have three boundary conditions, three equations, three unknowns. Everything is coupled, but it's still simple linear algebra. I have a bigger matrix, 3x3. I can invert it. And this is the final solution. It looks like it's the ugliest solution ever, but it's not so complicated, right? We are simply projecting the x and y component of the velocity on the tangential and normal and radial, because now I have two tangential components. So anyway, in our case, in the cylinder is a bit easier, right? Because the cylinder has the z-axis aligned with the Cartesian grid. So what we can do in the cylinder is we can effectively decouple the slip in z with the horizontal slip in xy. And this is what's written here, right? In the cylinder, we have nz that is 0, tz that is 0, and so there's a lot of things that cancel. And effectively, the uz here only depends on values that are interpolated with the z component, and these two are coupled, so it's a bit easier. Now, let's go back to our mean flow. What if we now compare quantitatively the experiments and the two methods? So we go back to this mean flow, we look at the low viscosity and high viscosity. So we have here the experimental data with the squares, and the lines are the methods. We can see that we can match quite well the Lagrangian mean flow with both methods. And if we decompose them, what we see is that we have here, so the weakly nonlinear analysis is in dashed black and in solid black, and the DNS are the color lines. And what we see here is we see the evidence of the counter-directed Eulerian mean flow, right? These negative values here. We can also match for higher viscosity. The match is not perfect, right? We are still working on it. This is also true for the Stokes contribution, and we are planning now to push a bit more in the DNS side to see if we can accurately match this supposedly true decomposition, right? Here we are trying to cross-validate the weakly nonlinear analysis. So now, If I have 5 more minutes, let me talk about another thing that we're working on with François and also with Clarisse Colombo, who is a master's student, which is on surface tension driven lateral breakup in T-junctions. So what are T-junctions? T-junctions are microfluidic devices that are built in order to generate drops. So in general, what you do is that you have a drop that enters the junction and that divides in two. This is for a standard T-junction. But what was shown in this experimental and theoretical paper is that with given aspect ratios between the outer width and the inner width and the height of your T-junction, you can show that you could have lateral breakup. And so instead of breaking the drop in two, you would break it in three, right? You see the drop coming from the top to the bottom. And here it's breaking laterally and symmetrically in both outlet channels. Here it's the same for a longer drop. And so there is a purely geometrical condition, beta, that predicts if the lateral breakup occurs or not, right? This is based on considerations on the curvature of the interface at the front and at the rear of the drop. This also happens only if you are below a certain capillary number, right? If you go too fast, then the drop will break in two, no matter if you are in favorable conditions for lateral breakup. And also depends on the length of the drop, right? A drop that is smaller tends to break in three easier than the longer drop. And so the idea here, that there is a model in this paper, right, that works quite nicely, but there are still some improvements that can be made. And the idea here was to try to replicate this numerically. This is quite hard numerically because you are solving a two-phase flow in a microfluidic setup, so you are at very low capillary numbers. You need to be careful that you have enough points in your thin film so that you don't have artificial contact lines that may occur that would lead to pinning and etc. So let's start first by looking at a central breakup. Here I'm looking at the top view. I'm looking at the setup from the top, and here the front view. This is what happens when you are in favorable conditions, but above the critical capillary number. So you go too fast to allow the lateral breakup to occur. And what you see is that the drop leaves a satellite drop, right, at the center, but there is no pinning of the rear cap when it enters, right? It starts to pin, but then eventually it goes down, and then it breaks in the center. Now, if you lower the capillary number on the same geometry, what you see is the following. You see the drop entering, and at the moment it enters, you see the rear cap that will remain pinned, and you see a pinch-off that occurs symmetrically on both sides, right? So this, I have to say that this is quite hard to find numerically because it's very sensitive to a lot of things, right? In the experiments, you have values of the capillary number based on the drop velocity, but you don't have flow rates, so you need to apply the correct boundary condition at the inlet, and so it's not so easy to find these transitions. Now, let me show first, finally, a small sketch of what's happening in this lateral breakup. So to repeat myself a bit, we have a droplet that enters the junction. The rear cap is pinned here. What you see here, you don't see, but there is a bypass flow that is forming a pocket here that allows this necking process to occur until final pitch-off because of the impossibility of the drop to stay as is, right? There is a difference in curvature between the rear and the front that leads to two daughter droplets. And so you break a drop into three. So let me finish with some remarks on what I showed in this talk. In the bouncing case, the numerical simulations gave us a broader view of what's happening. In particular, you could explain the experimental spread, the phase dependence. You could also extend the regime diagrams. And by monitoring meaningful quantities like energy budgets or the drop shapes by decomposing into spherical harmonics, we were able to cast a parameter-free model that could predict trajectories. So in the second case, the numerical simulation here served as a cross-validation of the mean flow decomposition predicted by a weakly nonlinear analysis. And we find a good agreement, right? We found these Eulerian contributions that are counter-directed or not, depending on the viscosity. And so here in this case, we were required to develop advanced numerical methods, right? It's not it's not trivial to model contact lines in 3D geometries. And in the last case, the T-junction, the fact that we are able now to reproduce microfluidics experiments will allow us to extend everything, right? We will look at, for example, the pressure distribution. Also, we can look at the velocities around the pockets that are formed by the bypass flow. And I think we will be able to improve existing models in this case. And with that, I thank you for your attention.
Merci. Question. Maurice. Non. Timide, c'est Maurice. Question en français. Donc, ta longueur de glissement de ta condition de Robin, là,
Ouais.
elle est mise partout, en fait, dans tout le domaine ou uniquement près de l'interface? J'ai pas bien compris.
Elle est localisée, en fait.
Elle est localisée.
Ouais.
Oh, d'accord.
C'est une longueur de glissement localisée.
Sur quelle distance elle est localisée?
Sur une distance, en fait, qui dépend de... sur une distance capillaire, en fait, sur 1 sur racine de Bond. Hop. Ouais, en fait, c'est le même modèle qu'on utilise dans la DNS, c'est le modèle de la weakly nonlinear. Où en fait, LZ dépend de la position de la ligne de contact, et on a une sorte de Dirac smoothé sur une certaine distance.
Heaviside, oui.
Ouais.
D'accord. Ok, donc ça c'est un autre modèle qui te donne cette distribution, et toi tu joues pas sur la
En fait, il y a plein de modèles, hein. On a fait d'autres études de modèles de ligne de contact avec différentes longueurs de glissement localisées. C'est un choix, en fait. C'est un choix, et du coup, c'est ça aussi qui nous permet d'étudier ce qui se passe à la ligne de contact et comment la dissipation joue un rôle dans le mean flow.
D'accord, du coup, tu n'as pas montré un exemple où il n'y aurait pas du tout ce modèle, que du no-slip?
En fait, c'est l'exemple, jusqu'à là, c'est l'exemple no-slip. Enfin, no-slip.
D'accord.
Il y a toujours du slip, hein, parce que sinon, ça ne bougerait pas. Donc, le truc, c'est qu'en fait, on a une no-slip, une condition limite no-slip sur les murs, mais dans les faits, on voit que l'interface bouge. Donc, il y a une vitesse non nulle. D'accord ? Et ce qui se passe, en fait, c'est que l'interface est advectée par la vitesse de la cellule mouillée, qui, elle, n'est pas nulle. Mais on ne peut pas contrôler. Et donc, en fait, c'est une sorte de glissement numérique qui dépendrait du nombre de points qu'il y aurait dans le système et qui est partout. Donc, ça, c'était des papiers de Stefan Zaleski et Sharia Afkami qui avaient montré que, en fait, ce qui se passe dans ces modèles VOF où on a la vitesse qui est centrée dans les cellules, c'est qu'on a une longueur de glissement qui est égale à la moitié de la taille de la maille. Et donc, en raffinant, on tend vers le vrai no-slip. Et l'idée, c'est ici de contrôler ce qu'on fait.
Très bien.
Mais j'avais une question sur la goutte qui rebondit.
Ouais.
D'une part, techniquement, ça veut dire que c'est très, très, très propre, non, la surface?
Oui.
C'est exceptionnellement propre.
Ouais, c'est du mica. C'est du mica, et donc on peut montrer qu'il y a des aspérités qui sont de l'ordre de dizaines de nanomètres. Donc c'est très, 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 très lisse. Ouais.
Okay. Et ma question, c'était pour la transition entre les deux phases. Tu peux remontrer la simulation, s'il te plaît?
Les phases, le diagramme de phase?
Non, la simulation.
Les
La
vidéos?
simulation. Parce que
les vidéos ou les images?
la simulation, les vidéos, oui.
Ah, les vidéos.
Voilà. Ce qu'on voit, en fait, c'est qu'il y a voilà, sur le band example, c'est qu'on voit ça reste attaché en permanence. Et il y a il me semble qu'il y avait un dimple, il y avait une zone qui est au centre, qui est un peu, qu'on voit à peine là.
Ouais.
C'est tout petit, et c'est ça qui fait la différence entre les deux cas.
Ouais.
C'est-à-dire cette zone-là arrive à se décoller ou pas. C'est vraiment une zone très très petite.
Oui.
Et ce qui me fait dire que peut-être il faut regarder des modes qui sont bien plus ADN, bien plus grands, pour voir cette chose-là. Parce que si tu as du mode que n égale 3, n égale 2, cette chose-là, tu auras du mal à l'observer.
Oui, alors, ce qui se passe, c'est que ici, donc, les tailles caractéristiques de ces films d'air, on est dans du 100 nanomètres, et puis quand ça passe en dessous d'une certaine taille, là, on a un contact, en fait. Mais ici, ce qu'on fait numériquement, c'est que on ne va pas pousser la résolution jusqu'à résoudre l'échelle la plus petite, qui est celle-ci, mais on va imposer numériquement une condition de non-mouillage. Donc, en fait, dans les faits, on est en train de sous-résoudre ce film d'air, et on est simplement en train d'imposer numériquement que ça ne touche jamais. Donc, la DNS, dans ce cas, c'est aussi un modèle en soi, en fait.
Et on voit les 2 points, là, justement.
Ouais, oui, mais c'est un artefact de visualisation aussi. Mais je vois ce que tu veux dire. Il faudrait regarder une simulation à très haut raffinement pour un cas précis, pour bien étudier la forme de l'interface proche du centre.
Ok, merci.
Ouais, je peux me poser une question, hein, euh, je réfléchis. Non, c'est que, ouais. Donc là, dans le Outlook, ici, quand on tilt le stage, en fait, on montre que ça va plus vite. Et donc ça, c'est compréhensible parce qu'on est en train de... La goutte se déforme plus que sur un bain liquide. D'accord? C'est le bain qui se déforme. Donc l'idée ici, c'est que bien sûr, on perd l'axisymétrie d'un système. Et si on voudrait modéliser, par exemple, la distance parcourue en fonction de l'angle du substrat, il faudrait prendre en considération des modes non axisymétriques, donc vraiment 3D. Et ça, c'est une question qu'on est un peu en train de se poser. Est-ce que c'est possible de faire quelque chose de similaire? Alors évidemment, on n'aura pas toutes les simplifications qui sont faites jusqu'à présent, mais est-ce que ce serait possible d'avoir ce sort de walking drop mode, il y a plein d'articles là-dessus, bien sûr, euh, dans un cas différent? Parce qu'en fait, il y a des cas qu'ils ont étudiés avec un bain liquide, où on génère des vagues, et ensuite, suivant l'impact de phase, si on est sur une crête ou sur un creux, la goutte va aller d'un côté ou de l'autre. Est-ce qu'on peut essayer de comprendre cette chose d'un autre point de vue quand on a un solide qui, lui, ne se déforme pas, et simplement par la déformation interne de la goutte? Donc ça, c'est une question qu'on se pose maintenant.
D'accord. Bah, alors là, j'avais une question très bête sur cet exemple-là.
Ouais.
C'est que, mais attends, il y a une couche d'eau, on est d'accord
Ouais.
dans ce cas-là. Mais expérimentalement, il n'y a pas de circonstance.
Oui, c'est ça le problème. C'est que donc, expérimentalement, il faut qu'on ait un truc assez long, ou alors il faut qu'on ait un inflow-outflow de telle sorte à ce que ce soit parallèle. Oui, bien sûr, c'est très compliqué de faire ça. Oui, bien sûr. Ouais. Oui, parce que là, c'est pas l'infini si on ne sait pas ce qui se passe. Ouais.
Une question sur
Il y avait des gens de Lille qui faisaient ça avec une goutte et en faisant vibrer du solide.
Des gens de...
Ils faisaient vibrer leur solide.
Ouais.
Et comme ça, ils arrivaient à faire se déplacer des gouttes.
Ouais, oui. Mais du coup,
C'est un peu... mais là, le solide se déforme et il y a une onde.
oui. Oui, parce qu'en fait, en théorie, si tout est parfaitement aligné, euh, la goutte reste sur place, en fait, elle ne bouge pas. Donc, dans les faits, il y a toujours un peu de désalignement, d'aspérité peut-être qui peuvent apparaître. Donc on a toujours un peu de mobilité, mais s'il n'y a pas de déformation et qu'on est complètement aligné, la goutte n'avance pas.
Question sur ce modèle, le modèle que tu as fait en se limitant au nombre à
Ouais.
quelques modes
Ouais.
et à l'équation que tu as pour l'évolution d'un mode en fonction du temps, dA1, dt,
Ouais.
voilà, typiquement. Là, dans le cas de droite, les oméga que tu prends, donc oméga 2 en l'occurrence,
Ouais.
donc ça correspond à une goutte dont l'état initial est quasiment sphérique.
Ouais.
Alors que dans tes simulations, il y a des déformations quand même importantes. Est-ce que ces effets non linéaires sont pertinents ou bien jouent pas en pratique?
Merci. Effectivement, là, on suppose que une description linéaire de ces amplitudes est suffisante, en fait. Mais si on regarde en détail ce qui se passe, c'est que principalement sur l'impact initial, donc c'est le moment où la goutte a le Weber le plus grand, dans des cas où elle ne rebondit pas plus haut que là où elle était, on voit qu'on on sous-prédit en fait ce qui se passe dans la déformation initiale. D'accord ? Donc la partie ici en pointillé, elle sous-prédit la déformation réelle de la goutte. Et ça, c'est parce que le modèle est incapable de faire en fait. C'est exactement ça, ouais. C'est qu'on est incapable d'aller aussi loin dans les déformations, où cette approximation n'est plus valide.
Ok, super. Merci beaucoup encore. Bravo.